we will start the afternoon session with Carolina Araujo from INPA, who is going to talk about the Calabi problem for Fano threefolds.
Thank you, Matthias. Well, so first of all, I would like to thank the organizers, not only for giving me the honor to be here at Fernando's birthday conference, but also for the opportunity of seeing so many good friends that I hadn't seen for a long time. It's really a very happy moment. I have to say that I was very touched by the video from yesterday from Fernando's students, and I felt that all they were describing about Fernando's soul is something that actually I could perceive myself from our interaction. So it has been a great pleasure to have your company, Fernando, for all these years here at INPA and in many different places. So thank you for your generosity, for your friendship, and for sharing with us your inspiring shine. And actually, I learned something about Fernando that I did not know yesterday, which is his endeavors in differential geometry. So I was not aware of that. And I was very happy to learn this because the topic of my talk today is related to differential geometry. So I feel it was a very happy coincidence. So I want to tell you today about the Calabi problem for Fano threefolds. So before I introduce what is the Calabi problem that I referred to, let me introduce the mathematician, Calabi, Eugenio Calabi. So he passed away last year in 2023 at the age of 100, and he left some very important contributions to geometry, and he shaped, in many aspects, he helped shape the geometry of the 20th century. And the problem that he posed that I want to describe is known as Calabi problem. So this was advertised in his ICM lecture in 1954. So this is the problem. Which compact complex varieties admit a Kähler-Einstein metric? So from its origin, we can see that the problem really comes from differential geometry. And this is a picture of a Calabi-Yau manifold. I will discuss this later on, but this is an example of a complex projective variety, a compact complex projective variety admitting a Kähler-Einstein metric. I'm going to explain what a Kähler-Einstein metric is. So maybe I give you here the plan of the talk today. So I will start by first describing the Calabi problem. And here I want to start from the very definition of the problem, the definition of a Kähler-Einstein metric, and then move all the way to the recent connections with algebraic geometry. So it started as a differential geometric problem, but we will see that it's very much related to algebraic geometry. And in particular, in the last 10 years, many tools from birational geometry have been playing a key role in studying the Calabi problem for Fano manifolds. And I would like to discuss a little bit about the birational geometry and the tools that we are using to attack this problem. And then maybe tell you in the end the state of the art in dimension 3. Okay, so let me start with the Calabi problem. So we start with Riemannian geometry. And so here we have a Riemannian manifold. So we have a smooth real manifold together with a metric G. And with this information, we can, as usual, measure angles and distance on the manifold. And we can define intrinsically a notion of curvature. So for instance, for surfaces, this gives us the well-known trichotomy between positive curvature, flat curvature, and negative curvature. So this trichotomy is going to appear later on. And so not only we can define curvature, but another important notion from Riemannian geometry is the notion of parallel transport. So with this data, we can we can transport vectors along curves so that they stay parallel. So these are some of the notions from Riemannian geometry that we are going to need. And now, in order to define a Kähler-Einstein metric, let me first define what is a Kähler metric, the Kähler condition. There are different ways of defining the Kähler condition. Let me start with the easiest one, and then we will get some characterizations. So here, this is the setup. I start with a compact complex manifold of dimension m. And so when I say a complex manifold, I just say that it's given by an atlas, but now the charts are identified with open subsets of Cm, and the transition functions are B-holomorphic. Now, the complex structure can be encoded, the way that we are going to encode the complex structure is by means of this linear function on the tangent bundle. So for every tangent space, we have a linear map, which is the multiplication by I. So this, I denote this map by j's, and it satisfies that j squared is minus the identity. So this is usually, this data is referred to as the almost complex structure. But in this case, well, this can be read off from the complex structure. So this is what we are going to use to encode the complex structure on this manifold. So we have a compact complex manifold, and here is I'm denoting by J this almost complex structure. And we defined a Kähler metric on X to be a Riemannian metric on the real manifold of dimension 2m that is compatible with the complex structure. So what does it mean to be compatible, for a Riemannian metric to be compatible with a complex structure? So this means that, well, first of all, the matrix is invariant by J, but also, and most importantly, that the complex structure commutes with parallel transport. So this is the definition of one possible definition of a Kähler metric on a complex manifold. And just a note, a compact complex manifold may or may not admit a Kähler metric. And when it does admit a Kähler metric, we call it a Kähler manifold. Okay, so this is the Kähler condition. I still have to get to the Einstein condition. And now let me give you some examples of a Kähler manifold. So first of all, the complex projective space is a Kähler manifold. It has what is called the Fubini-Studi metric, which is can be given very explicitly in coordinates, and it gives this is a Kähler metric on CPN. And more generally, if you have any complex projective manifold embedded in complex projective space, you can restrict the Fubini-Studi metric to X, and this gives X a structure of a Kähler manifold. So in general, algebraic manifolds are Kähler. But now, if you fix a Kähler manifold, so a complex manifold together with a Kähler metric, there are in fact many other metrics that can be put on X that satisfies this condition. So this space of Kähler metrics is an infinite dimensional space. And so the question is there any canonical Kähler metric that we can put on our manifold if it admits Kähler metrics? So before we answer this, let's look at the simplest example, which is the case of dimension 1. So if X is a complex projective manifold of dimension 1, so this is just a Riemann surface, and we usually have this classification according to the genus 0, genus 1, and genus greater or equal than 2. And here, I can always put these manifolds are always scalar, so we can in fact put many different metrics on each of these Riemann surfaces. But regardless of the metric that we put in it, we have the Gauss-Bonnet theorem that says that the average of the curvature can be computed in terms of the genus. So in terms of the curvature, this trichotomy here that I stated in terms of the genus can be rephrased in this way. So positive, 0, and negative curvature. Now, as I said, there are many different metrics that you can put in any given compact Riemann surface. However, there is a special one. So if you fix the complex structure, there is a unique Kähler metric on the Riemann surface with constant Gauss curvature. So you can make it constant equal to 1, 0, and minus 1 in these three cases. And so in this case, this is our canonical Kähler metric on the Riemann surface. Okay, so now we want to move to higher dimensions. So here, it is convenient to take another definition of a Kähler manifold. So let me start with any compact complex manifold X. And now, if you give me any Riemannian metric G on the real manifold associated to X, I can cook up a 1-1 form. So this is this form omega that I define here, which is just constructed from the Riemannian metric and the complex structure. And now, conversely, if you give me any real 1-1 form omega, I can compute back the Riemannian metric G. And now this is very convenient because now from the point of view of the Kähler, of the Chu form, the condition of being Kähler can be translated into the condition that the form omega is closed. And now when this is the case, we call it the Kähler-Chu form. And it then, because it is a closed Chu form, it defines an element in the second cohomology group. And so we are going to use this class, look at this class. But there is another form that we can associate to omega, which is the Ricci curvature form. So this is another Chu form that can be defined from the Kähler form omega. And again, this is a closed form. And so you can define its class in the second cohomology group. And now what is very remarkable is that regardless of which Kähler form you started with, once you take the Ricci curvature, this class does not depend on the metric. And this is nothing but the anticanonical class of X. So this is, in a sense, this is the higher dimensional version of the Gauss-Bonnet theorem that says that doesn't matter what the metric is, the curvature tensor is also defines the same class in cohomology. Okay, so now I can, we have this, I will define what is a Kähler-Einstein metric. So let's start with a Kähler manifold. So we already assume that the variety is Kähler. And if we fix any Chu form, any Kähler form omega, we can compute the Ricci curvature form. And we say that a Kähler metric is Kähler-Einstein if this Ricci form is a constant multiple of the metric. Now, we can normalize and take this multiple, this lambda, to be -1, 0, or 1. So we will always assume that we are in this case. And so the Calabi problem that was posed by Calabi in the ICM 1954 lecture was which compact Kähler manifold admits a Kähler-Einstein metric. And now, a remark is that if there exists a Kähler-Einstein metric, then it is essentially unique. And so in this sense, it is canonical as we would like it to be. But now, notice that, let's assume that our Kähler manifold admits a Kähler-Einstein metric. So let's assume that we have this condition satisfied. So this is saying, so the Ricci curvature, we have already seen that its class in cohomology is the anticanonical class of the variety. Now, the metric itself is positive definite. So we see that a necessary condition for the existence of a Kähler-Einstein metric is that the sign of the anticanonical class is well defined. So this is a necessary condition. If X admits a Kähler-Einstein metric, then either the canonical class is positive, and by this I mean ample, or it is numerically trivial, or the anticanonical class of X is ample. So these three varieties, I will be referring to them as canonically polarized varieties or Calabi-Yau type varieties when it's numerically trivial, and the Fano variety when the anticanonical class is ample. So we can then study the Calabi problem for these three classes of varieties, and the answer is different depending on the class. So in the 76, Yau proved this a very important result that when the canonical class is numerically trivial, then X always admits a Kähler-Einstein metric. And so this was a very, very, very important result that also had very important consequences also in algebraic geometry, not only in differential geometry. And then shortly after that, independently, Aubin and Yao proved that the same holds for varieties with positive canonical class. So canonically polarized varieties also, canonically polarized varieties also admit Kähler-Einstein metric. And now the only remaining class of varieties to investigate is the class of Fano varieties. And here things get much more subtle. So since very early, it was known that Fano varieties may or may not admit a Kähler-Einstein metric. The earliest necessary condition, or the earliest obstruction, is known as the Matsushima's obstruction. And it says that if a Fano variety admits a Kähler-Einstein metric, then its automorphism group must be reductive. Now, there are plenty of examples of Fano manifolds with non-reductive automorphism groups. So this gives us examples of Fano manifolds without Kähler-Einstein metric. So let me give you some examples and non-examples. So some examples of Fano manifolds with Kähler-Einstein metric. So the first one is the projective space. Again, the Fubini-Studi metric it's a Kähler-Einstein metric on Pn. More generally, any rational homogeneous space admits a Kähler-Einstein metric, and this was proved a long time ago by Matsushima. And also Matsushima's obstruction gives us non-examples. So if you take the blow-up of CP2 in 1 or 2 points, then the automorphism group, so these are Fano manifolds. These are Fano surfaces, which are called the Del Pezzo surfaces. And their automorphism group, because of that GA factor, that automorphism group is non-reductive. And so these Fano surfaces, they do not have Kähler-Einstein metric. Now, this is maybe a good time to state the classification of Del Pezzo surfaces or Fano surfaces. So there are exactly 10 deformation types of Del Pezzo surfaces. There is CP2, there is CP1 cross CP1, and then P2 blown up in at most 8 points in general position. So these are exactly the 8 types of Del Pezzo surfaces. Their automorphism group is very well known. So the ones that blow up at 1 and 2 points are the only ones with non-reductive automorphism group. All the others have a reductive automorphism group. And then there is this very important theorem of Tian and Yao. So this was proved in several different papers. They gave the classification of Del Pezzo surfaces that admit Kähler-Einstein metric. And basically what they proved is that the ones that cannot be Kähler-Einstein because of their non-reductive automorphism group, of course, are not, but all the others are Kähler-Einstein. So all the others admit Kähler-Einstein metric. But the proof was very different. It was really case-by-case analysis. And for instance, I think the last paper by Tian that finished the classification was a paper in Inventiones of almost 80 pages. So this was really difficult, hard analysis. So maybe I want to spend a few words talking a little bit about the analytic tools that were being used then to attack this problem. So let me describe them very shortly. So suppose we fix a Kähler manifold. And as I said, the space of Kähler matrix on X is an infinite dimensional. This is how differential geometers write this space. It's called the space of Kähler potentials. So this is parametrizing all the Kähler forms, the possible Kähler forms on X that define the same cohomology class as our initial form omega. So this is an infinite dimensional space. It can be given a structure of a hyperbolic symmetric space of infinite dimension. And now on this space, one can define a functional, which is called the Mabuchi functional. And a Kähler-Einstein metric corresponds exactly to a minimizer for the Mabuchi functional. So when people were proving back in the 80s, they were proving that a certain manifold admits a Kähler-Einstein metric. So often what they were doing is doing some really difficult a priori estimates to prove that the Mabuchi functional had a minimizer on this manifold. So this is sort of the point of view from differential geometry and from analysis. And now I would like to switch and tell you about what is the point of view from an algebraic geometer. And so this leads me to the notion of K polystability. So this is a sort of modern notion in algebraic geometry. And so let me define this very precisely. So we will always from now on, we will fix a Fano variety. So we can think of this as a smooth Fano variety, even though the theory has been extended also for singular Fano varieties. So we fix a Fano variety, and then we'll consider what we call a test configuration on X. So what is a test configuration? A test configuration consists of three things. So first of all, we have a family parameterized by A1. So this is a family of projective varieties such that the general fiber, for t different than 0, the fiber is isomorphic to our given Fano variety X. And then only at 0, the family degenerates to something. And this degeneration can be anything. It can be horribly singular, it can be reducible, can be anything. So this is the first piece of data, the family. But also on this family, I have this, what I call here an L. So the L is a relatively ample line bundle that on each fiber will restrict to a multiple of the anticanonical class. So this is a relatively ample line bundle, and on each fiber, it's a multiple of the anticanonical class. And then finally, on all of this, I have a C star action. So this data is what we call a test configuration. Now, for any test configuration, we can define what is called the Donaldson-Futaki invariant. So this was originally, it was defined by Tian in terms of the weights of this C star action. But then later on, Donaldson reinterpreted this invariant in terms of products of cohomology classes. And so I thought about just saying that I will not define what this is, but I decided to, since I think it is, okay, here's the definition. This is at least Donaldson interpretation in terms of intersection of line bundles. But really what I would like you to keep in mind is that what does this Futaki, the Donaldson-Futaki invariant really means? So let me explain that to you. So we have this family parameterized by A1 that is, okay, over t equals to 0. This degenerates into something. And for all other values, this is our variety X. So what we can do is we can use this relatively ample line bundle L to embed this in some big projective space. And then and here, let me here write down the schematic. This is my H, my space of scalar potentials on X. So here what I can do is the following. So I use this L to embed in Pn. And then on Pn, I have the Fubini's 2D metric on Pn. I can pull it back to X. And so this will give me a scalar metric here, omega t. That it's a point on the scalar, the space of scalar potentials. Now, when I vary t, this metric varies, and this defines an infinite geodesic ray in the space of scalar potentials. And what this Fubini Donaldson-Futaki invariant is just the limit of the derivative of the Mabuchi functional in this infinite ray. So here we have the Mabuchi functional defined here. And then when I take the limit of the derivative along this ray, this is exactly the Donaldson-Futaki invariant. So remember that we are actually interested in Kähler-Einstein metric. And I mentioned that the Kähler-Einstein metric corresponds to a minimizer of the Mabuchi functional. So if the Mabuchi functional has a minimum, this derivative cannot be negative. So we see that if X admits a Kähler-Einstein metric, this Donaldson-Futaki invariant is always greater or equal than 0. And in a sense, this is the starting point for the definition of K polystability. So Okay, so this is the definition. So again, I fix a Fano manifold, and then I have already explained to you what a test configuration is. We say that X is K polystable if for every non-trivial test configuration, first of all, the Donaldson-Futaki invariant is greater or equal than 0, and it is 0 if and only if the central fiber is actually isomorphic to X, so there's not really degeneration. And so, as I explained, it's not difficult to believe that if X admits a Kähler-Einstein metric, then X is a K polystable. And it was conjectured by Yao, Tian, and Donaldson, this was a very important conjecture, that the converse is also true. So X admits a Kähler-Einstein metric if and only if X is K polystable. And well, I stated this is a conjecture, but in fact, this is now, for about 10 years, this is a theorem by Chen, Donaldson, Sun, and then proved also by Tian in 2015. So they proved this equivalence, and this is really a remarkable result. So this is saying that the existence of a Kähler-Einstein metric, which is an analytic condition by definition, in fact, is an algebraic condition. This is a condition that can be defined in terms of algebraic geometry. So if you think of this geodesic rays in the space of Kähler potentials, what this is saying is that to check that there is a minimum, it is enough to check the rays in algebraic direction. So let's put it this way. Okay, so this was really a very important result. And then, of course, it does not tell you how to check if something has Kähler-Einstein metric, not yet. But that led many algebraic geometers to start working on K polystability. And in particular, birational geometers started to work on it. And so let me now take a little break from the Calabi problem and introduce some tools from birational geometry. So let me recall that the minimal model program in algebraic geometry, so this is a program that it has the goal of classifying projective varieties. And what it does is that given a projective variety X, it tries to find a simplest representative of X in its birational class. And I will refer to this simplest representative as a minimal model for X. So in dimension 2, okay, in dimension 1, it's not really interesting. So isomorphism and birational equivalence is the same for a smooth projective curve. So let's start with dimension 2. Now, in dimension 2, the minimal model program was developed by the Italian school. It was completed in the early 20th century. And in this case, the operations that lead you to a minimal model are very simple. These are just blowdowns. So what the minimal model program for surfaces says is that if you start with any complex projective surface, you start by doing blowdowns, suitable blowdowns, and then after finitely many blowdowns, you get to a minimal surface. So this is the simplest surface in its birational class, one that cannot be further blown down. Now, in higher dimensions, the problem is much more difficult. So it was in dimension 3, it was established by, well, it was work of a lot of people, but then was finally finished by Mori in 1988, and this earned him a Fields Medal in 1990. And then in higher dimensions, this was, well, the program is not completely finished, but there has been important developments that give us minimal models in many cases of interest, and this was the important work of Birkar, Caccini, Haken, McKerner. And so as a consequence of the minimal model program, we can state it simply as saying that every projective variety can be constructed from 3 classes. And these are exactly the 3 classes that we have encountered earlier: canonically polarized varieties, Calabi-Yau type varieties, and Fano varieties. Now, if I go back here, you see that we had to wait many decades to go from dimension 2 to dimension 3. And this is really because in dimension 3 and higher, the techniques that one needs are very different, and they're much more complicated than in the case of surface. So the first difficulty that one has to accept is that singularities are unavoidable. So even if you're interested in classifying smooth projective variety, you have to allow for singularities in order to be able to find a simplest representative. And so the first difficulty was, in fact, to define the correct notion of singularity. So now these are notions that are very well known in birational geometry now: terminal singularities, canonical singularities, Kawamata log terminal, which we often refer to as KLT singularities, log canonical, and so on. And I should stress that it was not immediate to get to the right definition of the singularities. So again, let me give you an example of how we define these notions of singularities. Let me have here three increasingly complex singularities. So let me start with, say, a smooth point on a surface, a smooth point, say, in P2. And then I'm going to take here a singular quadric surface, and I'll say a cone over, say, an elliptic curve. So this, it's getting the singularity is getting more complicated in this way. And now let me consider the blow up of this singular point. So here I have the exceptional divisor, and here let me call x tilde. Now, if you take a Chu form defined, a non-zero Chu form defined on a neighborhood of this point, for instance, if I write it, let's say dx, y, this dx wedge dy, if I write down the local form of the blow up and take the pullback of this Chu form, so if I do the pullback, we will get that this will pick up a 0 along the exceptional divisor. So this is an easy computation that one can do. So this is the local description of the blow up. So if you pull back this form, then you get this one here, which has a 0 along the exceptional divisor. So we often write this in terms of the canonical class. This is how we express this. We say that the canonical class of x tilde is the pullback of the canonical class of x plus e. And so here, this coefficient here of e is what we usually call the order of the relative anticanonical, the order on E of this relative anticanonical, so this would be 1. Now, if you do the same here for the quadric cone, if you write down, we can write down, for instance, exactly this form here, and pull it back to the resolution. So here, again, I can blow up a point, and I get a smooth surface. But now, if I do this, if you write down, if you compute the pullback of the Chu form, you see that it does not have neither a pole nor a 0 along E. So this is how we actually express this, or that the order of the anticanonical at the E is 0. And if you do the same thing for the cone over the cubic curve, what you get is, again, you start with this form, you pull it back, and then you will see that it will pick up a pole along the exceptional divisor. So here is the E. And now this one here will pick up a pole, so this express it in this way. And so we can use this coefficient of E in order to measure how complicated the singularity is. So here the order is 1, here is 0, and this is -1. So now, in general, let me define what we call the log discrepancy. So here, I take any birational morphism to x. So in this case here, we had the blow-ups. And then I take any prime divisor on this birational model. And then I define what we call the log discrepancy. Well, there's, for technical reasons, so we add this 1 here. So this is 1 plus the order along the exceptional, or along the divisor of the relative canonical class. So this was exactly what I was doing here. And so here, the log discrepancy would be 0, this would be 2, 1, and 0. And in fact, this does not really depend on the divisor, but it only depends on the valuation associated to a divisor. So any divisor on a birational model of X defines a valuation on the function field, and this log discrepancy only depends on this valuation. And so we say that a variety has KLT singularities if for every birational morphism and for every value, in fact, for any valuation or any prime divisor on X tilde, the log discrepancy is greater than 0. So these two are KLT, and this one is not KLT. And it turns out that this is the best notion that one can impose on singularities in order to have the minimal model program. So birational geometers have been dealing with these types of singularities for several decades now. And now let me define a generalized version of Fano variety. So I call a Q Fano variety a projective variety that is possibly singular, but such that the anticanonical class is still ample, and it has at worst KLT singularities. So these are the singular Fano varieties that, in a sense, are well behaved. And before I say this, let me just mention that the work of Bierkart, that earned him the Fields Medal in 2018, has to do exactly with studying these objects, Q Fano varieties, and some restrictions on the singularities and some the structure for the space of such varieties. So this is something that we will use later on for the Calabi problem. And now, starting to relate to the Calabi problem, the first hint that birational geometry could be used to study the Calabi problem came from this result of Li and Xu in 2014. So they show that when you want to test K-Pauli stability for some Fano variety X, it is enough to consider spatial test configurations. So spatial test configurations just mean that this spatial fiber here is always a Q Fano variety. So in principle, you would have to test for any degeneration, but it turns out that it is enough to check for these very well-behaved degenerations, Q Fano varieties. And so since then, I think then people started to actually dig into this. And nowadays, we have some very nice and effective valuative criteria to check K-Pauli stability, or equivalently existence of Kähler-Einstein metric. So let me state one such valuative criterion. So here I'm fixing a birational morphism and then a prime divisor on X tilde. We have already defined the log discrepancy of X along E. And let me define another invariant, which is, well, it's called the expected vanishing order, which is this integral. So it is 1 over the top self-intersection of the canonical class, or the volume of the anticanonical class. And then I integrate the volume of this line bundle here. So I take the pullback of the anticanonical class, and then I subtract t times the divisor E, and then I integrate this. So I wrote this as an infinite integral, but in fact, this integral is finite, because if you make t very large, then the volume is going to be 0, because there will be no section for this line bundle. And so there is this threshold, which is called the pseudo-effective threshold of E. So this is the soup when you still have something pseudo-effective, and so this is, you can integrate only up to tau V. Okay, so we have this, and now I can state the Fujita-Lee valuative criterion. It says that a Fano variety is K-semi-stable if and only if the log discrepancy is greater or equal than the expected vanishing order for every exceptional divisor E. Now, this looks like a very difficult condition to check, because you have to check this for every exceptional divisor, or for every divisor on every model over X. But at least this gives us a very nice criteria to say that something does not have a Kähler-Einstein metric. Because if I can exhibit one single divisor E for which this inequality is violated, then there can be no Kähler-Einstein metric. And this is actually a very useful way of showing that something is not Kähler-Einstein. So there are also some positive criteria that I'm not going to have time to discuss. But now maybe this is a good point to go to the third part of my talk, which is now with these tools, how can we actually, for instance, solve the Calabi problem for funnel threefolds? So let's see. So at this point, we are now in 2020, there was, with all this developments about K-stability, there was this very nice conference in the American Institute of Mathematics called K-stability and related topics. So people were getting together to discuss this notion, and there were talks in the morning, and then in the afternoon there was some group, some research groups, and each one was trying to solve a problem, and then some of us actually got together and decided to solve the Calabi problem for funnel threefolds. So we understood that with the tools that were available then, there was a chance that we could actually solve the Calabi problem for funnel threefold. So what does it mean to solve the Calabi problem? So, okay, so this is the funnel team. So these are my co-authors. So it's me, Ana Maria Castravet, Ivan Chestov, Kento Fujita, Anne-Sophie Kalogiros, Jesus Martinez Garcia, Konstantin Shramov, Hendrik Soos, and Nivedita Viswanathan. So we started working on this problem at the AIM. And then the pandemic came, and then during the first year of the pandemic, we were working on this. And then finally, we have our theorem. And to state this, let me first remind you the classification of funnel threefold. So this was, I told you for surfaces, we had 10 deformation types of Del Peso surfaces. For funnel threefolds, we have 105 deformation families. Each one of them are defined, are explained quite explicitly. So there is this site called the Phanography. So if you go to Phanography, there is the list of 105 deformation families, and for each one of them, there is a description, a birational description, the description of the automorphism group. There's a lot of information about each one of them. And then, so we want to understand which one of them admits a Kähler-Einstein metric. And let me already point out that something here happens that it's different than the case of surfaces. Already for threefolds, there are deformation families for which there are members that admit Kähler-Einstein metrics and members that do not admit Kähler-Einstein metrics. So this did not happen for surfaces, but for threefolds, it does. And so the problem is really more complicated. And then here is our theorem. So for each one of the 105 deformation families of three-dimensional funnel varieties, we determined whether or not the general member admits a Kähler-Einstein metric. So as I said, this is not all members, but the general member admits a Kähler-Einstein metric. And for 78 of the families, the general member admits a Kähler-Einstein metric, while for 27 families, no member admits a Kähler-Einstein metric. So I should say that many of these examples were already known when we started to work on this. So 65 cases were already known. And so we actually worked only with 40. There were only 40 cases to work on. So let me first tell you something about the previously known cases. So the previously known cases, so there were many specific criteria that we could apply to certain varieties. For instance, I have already mentioned that if the automorphism group is non-reductive, then there's no Kähler-Einstein metric. So those were known. Also, for products, the problem is very simple. So a product of two funnel varieties has Kähler-Einstein metric if and only if each one of the factors has a Kähler-Einstein metric. For toric varieties, there's beautiful combinatorial criteria. So if a funnel toric variety corresponds to a certain polytope, and the condition of admitting a Kähler-Einstein metric is equivalent to saying that the barycenter of the polytope is at the origin. So something very easy to check. And so among the 18 toric funnel varieties in dimension 3, 5 admit Kähler-Einstein metric, and 13 do not admit Kähler-Einstein metric. Also, cyclic covers, also again, there are criteria for cyclic covers of Fano varieties. And also there was this class of varieties called complexity 1 T varieties. So these are varieties that admit a torus action, a torus of dimension 1 less. So still there we have a lot of combinatorics that can be used to understand the K-poly stability for this variety. So these were more or less the known cases can more or less be divided into these classes. And now let me just briefly mention the tools to prove K-poly stability. So first of all, I have already mentioned the Fujita-Lee valuative criterion. So a Fano variety is K-stable if and only if the log discrepancy is greater than expected vanishing order for any valuation. So in the previous theorem, I said that 27 out of 105 do not have Kähler-Einstein metric. So among these 27, for 26 of them, we could find a divisor violating this condition on the variety. It was not even, we didn't even have to go to a blow up. Already on the variety, there was always some suspicious divisor for which you can compute, and then it would violate this condition. So for those, we can prove it, showing that it's not Kähler-Einstein. Usually, it's much simpler. Now, to prove that something is Kähler-Einstein, then, I'm just going to mention a bit the tools. So there is this notion of a stability threshold. So this is the infimum for all divisors E of the log discrepancy divided by the expected vanishing order. So we have to prove that this is greater than 1 if we want to win. But this stability threshold admits other characterizations in terms of log canonical centers. So this was where a lot of the work of Birkar is used to give another interpretation of this stability threshold, and also some estimates, a priori estimates for this threshold. So there is this theory which we call Aban-Zhuang theory of admissible flags. So this was introduced a few years ago by Aban and Zhuang, and it turns out that this is a very efficient way of estimating this stability threshold, and then if we can estimate it that this is bigger than 1, then we win. And so this is what we use, but we actually don't have to even to do that much work, because also there is what we call an equivariant valuative criteria. So what does this mean? So this means that if your Fano variety has, say, a big group of symmetries, you don't have to test these inequalities for every E. You just have to test it for invariant divisors E. So usually, if you can choose a variety with big symmetry group, you have much less work to do. And now, K-stability is an open condition. So I wanted to check which general members admit Kähler-Einstein metric, but then because this is an open condition, it is enough that I prove it for 1. And so what we do is we explore symmetry. So often when we are working with some of the families, we pick some specific member that has a bigger symmetry group, and then we compute these estimates for this specific member, and this automatically gives us K-stability for the general member of the family. Okay, so this is more or less some of the ideas that we use. So this was a really long work, so we could not have it published in a paper. So we wrote a book about this. So this was published last year. And there is a copy at the INPA library, so in case if you are interested. And this is what I wanted to tell you. And feliz cumpleaños, Fernando.
Comments or questions?
So in the case where the general has one and the special don't, do you have an idea of the codimension of the complement? Like a Nether-Lefschetz locus, something like this?
So for the cases where you have both cases, so in the book, we have some specific conjectures for each one of the families. So in some families, we actually know exactly which ones are K-polystable and which ones are not. And for the other ones, we have conjectures. Some of them, the easy ones, have been proved since then, but I think there is some of them are not yet known. So this one is which one? This is which family are you thinking of?
Well, maybe I was thinking of the ones with rank 1,
I would have
prime Fano threefolds. Rank 1 with ample anti-canonical bundle.
Yeah, so yeah, one would have to look at the list. So there is this one case, the V22, it's the most complicated. Donaldson already was looking into that, but I don't know it by heart. I would have to take a look. Sorry.
Thank you.
Okay, so it's almost the same question, actually. Do you know which families that have a general member which is K-polystable, but there is a member or not, if it's...
Yeah, no, we know many cases that we can, for instance, there is this V22, there are some members with non-reductive automorphism group. The general member has reductive automorphism group, but the other one does not. So so in some cases it is easy. For instance, in many cases when you have a GIT construction, the stability is the same as the GIT stability. So for cubic threefolds, the K polystability is the same thing as GIT stability, and this is still the case in some specific examples. But then at some others it diverges. So in some cases we do know, but we still, I should say that maybe the Calabi problem for Fano threefolds is not completely solved. There are still some families for which we do not know a fine description.
Okay, thank you.
More comments or questions?
What about fourfolds? Is there anything?
So, fourfolds. There is not even people don't even expect that you will have a list of fourfolds. So there I don't know, thousands of fourfolds known, but there is still not a complete classification. So I don't think that the right question would be try to go to fourfolds, but I personally think it's an interesting problem that I'm looking at is to look at some families of funnels that you can generalize to arbitrarily large dimensions. So for instance, we can construct one specific case that I'm looking at. It's say you blow up Pn at n plus 3 points, you do some flips, then you get to a very nice funnel. So for any even dimension, this is a smooth funnel. And then it makes sense to ask, is it K polystable for all of them? And so I think this is more or less the direction that I think it's more feasible to have some families of funnels that can go to arbitrarily large dimensions and for which you have, or not, the notion, the case of K polystability.
More comments or questions? Well, I do have one. Maybe you already said that, but I got a bit lost with the following. You said that for the positive cases, you managed to pick a nice representative with nice symmetries to reduce the problem and show that this infimum was over 1. And for the negative cases, you found a nice divisor. But this, you said, killed 26 out of 27 cases. So what do you do for this extra?
Well, this other one, it's not a divisor that you can find on the variety. You have to blow up a curve, and then this will be the exceptional divisor over that curve. So this was the only one case where you could not find the bad divisor on X. But you had to blow up something that, again, it was something that was very obvious. It was a very special curve. And so just blow up and compute, and then that gives the inequality.
I see. Thank you. Well, one more question over there.
Going from bed divisor to bed tested generation.
Sorry?
Here you have a microphone.
The criterion is existence of a bad test configuration, and you say there's if some bad divisor, then you can show it. If given a bad divisor, can you construct the best test
Well, I
configuration? How you
cannot,
do
but
it?
it can be done.
Yeah, but
I don't know how to do
what's the
this.
idea how to go?
Yes, but there's no, people know how to do it from the valuation, from the divisor E, one can actually cook up the test configuration.
Yeah, and this Aban-Jean criterion is like given a flag, you construct the generation. That's the idea.
No, this is a technique to estimate this stability threshold. And so it will give you some lower bound on the stability threshold, but in some cases this is already bigger than 1, and then you win.
So there's no degenerations involved
No,
in this
no,
theory.
no, not really, yeah.
Okay, well, if there are no more questions or comments, let's thank Caroline again.